of you, especially in the front. Plenty of seats here in the front. There's a spare seat. Can you please move together? There's a spare seat. Can you please move together? There will be people coming late, so let's give them the opportunity to find an easy seat. Okay? So spare seats. Can you please move together? Can you please move together? Have fun of this. So guys, we have, for those of you, so we are now getting to the end of the seats. We are live streaming this lecture. There's still seats although here in the front, okay? So those of you who are still here. We're having a live stream into Stopford Theatre 1 for those who are looking for seats. Can you please listen to me? There's a live stream into Stopford Theatre 1, and we have, Andy here has little sheets of paper with a YouTube address where you can see the live stream. Okay, if you're coming now and you're not getting a seat, Andy has little slips of paper with this information. Okay, we are live streaming this into another lecture theatre. Andy has the information, and we're live streaming it via YouTube, so you can use that. There's still a spare seat over there. Guys, can you please move together? I know you're trying to avoid looking at me. Can you please move together? There's a spare seat. Third row from the top. Yes, you in the white jumper, exactly. Okay. So you can get the information, the room information for the live stream and for the YouTube link is with Andy over there. Okay, we are live streaming this into another lecture theatre. Andy, can you move over there and help? I think the guys up there and on the top, I think they need the information. Okay. So guys, Andy here has information, has this information. You can get a slip of paper from Andy with this information for the live stream and for the lecture theatre in which we are streaming this. Okay, you can sit in the coffee shop, and Stopford is opposite the student, if you go past the student union on the left-hand side. Okay, so Andy is still going around with the information where we are live streaming this to and the YouTube address, okay? And of course the recording will be available afterwards. Anyway, so today we're going to talk about functions and roots of functions. Although some of this is just a revision, some of it I will refer to you to Blackboard material afterwards. But before we do this, we had a quiz on Piazza, and of course the recording will be available afterwards. Yeah, okay, that's the live stream. Sorry. Let me switch it off. I was just checking that it works. Works with a half-minute delay. So, we had this quiz up on Piazza after last week's lecture. And it was a quiz to test your understanding on necessary and sufficient conditions. And I just want to review this quiz because it is important. But before we do this, let me explain to you why this issue about necessary and sufficient conditions is important. I told you last week that the main part of this course is about finding maxima or minima of functions. Okay? And it's so far what you've done, most likely in your previous studies, you've done some sort of, you just need to log into Piazza to see that. Okay? And those of you who haven't registered with Piazza, please do that. follow the link on the Blackboard side, okay? And then you can see all that information. So, remember I said the main purpose of this course is to figure out techniques to find optima, minima or maxima of functions. Many of you will have done that already, even in school, in college, or in introductory maths. And you would have typically done it with functions where you can sort of print the functions and you can confirm the results. But in this course, we're going to learn about the techniques which we need to optimize functions when the functions are so complex that we can't really think about them, because potentially they live in a 5-dimensional world, because we may have five input factors, okay? Although we'll use the techniques only with 2 input factors, but they're generalized to 5. And then you can't even plot the functions anymore and can't possibly confirm that something is a maximum or minimum. So we have to learn techniques where we can confirm whether something is a maximum or minimum without sort of looking at the function. Now imagine the following. Who of you likes hiking? Raise your hand. Okay, super. Oh, a few of you. Here in the front. Now, if you go, think about, and this is now a really useful analogy, okay? Think about you're wanting to climb a mountain, but it's totally foggy, okay? So you can't see anywhere. How do you do that? I'm putting you on the spot, sorry for that.
There are usually poles. And then on our tracks, there's on one side.
Brilliant idea. Okay, so there are usually tracks and there are poles. You just need to see the next pole. Let's say it's too foggy to even see the 50 meters to the next pole. How do you find the top of a mountain? Let's say you are on a spot. Which direction would you go?
Well, I look for the mask. So where the mask is, that's north. And then
okay, that's right. You can look at the tree trunk, let's say, and see where the moss is. Yeah. Yeah. Let's say there are no trees. You're too high, yeah, and there are no trees. Okay?
So it's not a mountain.
Any other ways? Anyone have any ideas how you could find to the top of a mountain? Yeah.
You go incline, like where the mountain shapes upwards.
That's right. You stand on the spot, and perhaps you feel around with your feet and check out where is it going up. And what's the steepest way up, perhaps even, and you go this way. And how do you know that you found the top of the mountain? There's no way up. Whichever direction you look, you feel with your feet, it's going down. You know you found a top of the mountain. Brilliant. This is exactly what we do. This is why we look at derivatives, because they look at the slope, right, of a function. And that's why we will also look at the second derivative, which tells us something about the curvature of functions, because that will tell us whether where we are sort of on a, the shape is such that it only goes down. Okay, that's why we look at the second derivatives. But now, remember, it's so foggy, you can hardly see the hands in front of your face. What could have happened? Where could you have ended up? Sorry? You could have ended up, which to you feels like the top of a mountain, but let's imagine the fog is all of a sudden lifted, and just 100 meters further in that direction, there's actually a higher point. It's just that first you have to go a little bit down, and then further up again. Okay? So, the reason why we need to understand about sufficient and necessary conditions is because we will learn about conditions which we can establish, sometimes not, that will confirm that if you have found a little top, then you know that this is overall the highest point, even though you can't see anywhere else. Okay? So think about this. These are techniques which we will need to help the climber in the fog. Okay? If you're on such a complex mountain that you really can't look at it, but there are some conditions which can be fulfilled sometimes, which will then tell you that, okay, if you found a little top, then this is really the maximum. Okay, that's why we need, you don't know what these conditions are yet, because we are not that far, that's at the end, towards the end of the course, but that's why we need these conditions. So with this in mind, let's look at this little pole. Okay, here it said, the necessary condition for you to pass this course unit is you come to lectures, every Tuesday you eat pizza, you understand derivatives, you come to see me in my office hours. Okay? So what does it mean, a necessary condition? It means this puts sort of restrictions on it. It means you can't possibly pass this course unless you do one of these 4 things. Okay? Now, of course, you can pass this course if you do not come to lectures, because we have brilliant lecture podcasts, okay? We have a good book, textbook. None of what we do here is outrageous and nobody else will tell you that. Of course you can pass this course without coming to lectures. I think lectures will help you learn, okay? But you can pass. So is the first one a necessary condition? No. Okay? What about the second one? Clearly not. Okay, although it's fun, okay, to eat pizza regularly. What about the third one? Absolutely yes. Nothing in this unit works without understanding derivatives. I can guarantee you, if you don't understand derivatives, there is no chance that you will pass this course. So that is indeed a necessary condition. Someone may quibble and say, oh, perhaps in the exam I can guess enough right answers and I may become lucky. Okay, that's fine. But essentially, this is a necessary condition. Okay? What about you come and see me in my office hours? What do you think? Is that a necessary condition? No. Okay, plenty of you will pass without me coming to my office hours. Okay, does that all make sense? Any questions with this? Okay, it's perhaps best to understand necessary and sufficient conditions if you either remember this example or another sort of fairly simple example to explain it to yourself. Okay, it's best explained by an example. What about what about, it was this one. Here, quiz on sufficient conditions. What's a sufficient condition for you to pass? So, a necessary condition, let's go back to the other one. We said understanding derivatives was a necessary condition. Does that mean that if you understand derivatives, that for sure you will pass that unit? No. Okay? That's why it's only a necessary condition and not a sufficient condition. Sufficient conditions are those that if they are met, then you know that whatever is the topic here, passing that course will follow automatically. Okay, so with that in mind, what is a sufficient condition to pass this unit? You get an exam grade of 42. Is that a sufficient condition to pass this unit? Yeah. Yes. Why?
Because if you get close to pass
that it's over 40 and the exam is only 95% of the grade, but even if you don't do the online quiz and therefore get 0 on the online quiz, 0.95 times 42 is still at least 40 and therefore you pass. Okay? Good. So this is a sufficient condition. Is it a sufficient condition to make an effort? No, not quite. Hopefully I'll try to help you to make sort of well-directed efforts and then I hope it will work out. But just making an effort isn't good. You also have to evaluate how am I actually understanding, where am I struggling, I need to ask someone. You have to make the right effort. Okay? Is it sufficient to attend all lectures? Is that a sufficient condition? No. If you just come here and put your ear onto the desk, that's not good enough. Okay? And you read the lecture notes, again, clearly not a sufficient condition. Just because you read through the slides and whatever, even the textbook, that by itself doesn't mean anything. Okay? You need to try and understand what's in there as well. So sufficient condition means if that is true, so if you have 42 in the exam, then for sure you will have passed this unit. Okay? And this is what we'll be looking for later when we try and find a maximum. You may have found a little maximum, we'll call that a local maximum, but what you really want is to understand whether this is also overall the maximum. And what we are looking for is sufficient conditions. Okay? If another condition is true, then that will guarantee you that that little peak which you found is also the overall peak, or what we call the global maximum. Okay, so that's why it's important to understand these concepts. Any questions? Okay, so what we're going to do today is we're going to talk about a little bit about functions, equation and quadratics, although I will just refer you to what you've done previously, and there's an online clip to remind you of things. Polynomials, exponential and logarithmic function, they're very important, so we need to understand some properties, although most likely, as usual, I will not go through everything in detail in the lectures, and I'll refer you to online clips that go through stuff in detail. So, we really need to understand what functions are, okay? Because that's, we're going to be talking the language of functions here. They are super common in economics, okay? In economics, we know as economists, whenever we build models, and we talked about this last week, we're really sort of building a little simplified version of the world. Okay, and it's going to be super simplified because the world is so complex, we can't possibly hope to capture it all. Hopefully a world that is, despite being simplified, still captures very important features of the world. And the way how we formalize the world in most of economics is by using mathematical representations of behavior and then also of outcomes. So and you will have learned already most likely about demand functions, and if you haven't had economics at your A-level or college, perhaps not, and that's perfectly fine, then you will learn about them. Demand functions, cost functions, revenue functions, profit functions, okay? And so whatever we are interested in, we'll formalize in functions, and if we are then interested in maximizing or minimizing something, we'll be trying to either maximize or minimize such a function. And then we'll do that mathematically, okay? So this is why we desperately need functions. So, a function is really nothing else but a rule. So some of this is going a little basic perhaps for some of you, but it's really important to understand the basics here. Okay? So if you take a number x and then design it to a unique other value, so we're taking x, we are sending it through a function, and that will then deliver a value, and we often call that value y, okay? But not always. We can give this, we can turn it around. We can put y as the argument into the function and x as the output, okay? Or could be p and q, or for price and quantities, or it could be any other thing. So don't be fixated on this always being y and x. So the rule is given by that f, by that function. And that's just an abstract representation of a function. It doesn't tell you exactly, if it just says f, it doesn't tell you exactly what that rule is. Okay? That's why we then have to actually write down a particular function. But it tells you what needs to be done to that value x in order to obtain the output. Okay? And then the result of this, the result of applying the rule, will deliver one number. And that's important. Okay? That is only one number. So whenever you put something into the function in, there can be no doubt about what you get out. We call that x here, we call that the argument of a function. Okay? And that's an important vocabulary for you to know because I will use it quite often. So let's use an extremely simple example. Okay. Let's use as that rule f of x, x squared. Okay. And our argument x, we say, comes from this element of R. What is that R? real numbers. Okay, good. Any real numbers. Could be x, could be any real number. So if you do that, if you plug in 2 as x, so we now plot x on the horizontal, and the outcome of our rule, f of x on the vertical, if you plug in 2, we get 4. We get this point. If we plug in negative 2, we also get 4. Because the squared, so we're here. And of course, you can do that with all sorts of other values. 3 will be 9, negative 3 will be 9. And if you do that, what you will find is, of course, the well-known quadratic function. Not particularly pretty the way how I drew it, but you get the drift. Okay, that should not be a surprise to anyone here. So, of course, most rules we're going to be dealing with will be more complicated. Okay, so let's say here the function is x squared minus 2x plus 1. There's a typo here. This should be an x. Okay. So this is just saying what I just called, don't be fixated by the by the x. That could be anything else. Okay, and also the name of the function, which we typically call f, but that could also take any other letter. Often it's g8, sometimes we call it, if it's a profit function, the profit function. Okay, so sometimes you will see that here we said x could be any real number. Sometimes we restrict x to come from a certain range of numbers. Okay? Here, for instance, from the range from 0 to 4, what does the square bracket mean as opposed to the round bracket? Anyone remember? So the square bracket means it includes 0. If it was a round bracket, it would exclude 0. Okay? It would say anything above 0. And the same here. The square bracket includes 4. A round bracket would exclude 4. Okay? So anyone who's not taking notes now even thinks this is damn easy, or you're missing out on important stuff. Okay? So sometimes we restrict this. Why may we want to restrict arguments to a certain range? Can someone think of an example? And like an economically important example. Yeah? Pardon me? That's right. Prices. If the input, super. If the argument is price, can we think of negative prices? It's difficult for most markets. Okay? Can milk be a negative price? What would that mean? Someone would give you money to also take the milk. Okay, doesn't make sense. Are there markets with negative prices? Someone think of a market with negative prices? Yes? Who was that? Yeah?
Like, for example, selling garbage.
Selling garbage?
Yeah, for example, in Norway, I think, or Sweden, they dispose it.
So you are selling garbage, but you have to give money to someone to take the garbage, so they dispose it, especially if it's like poisonous stuff, for instance. Oh, it's super. That's a super example, okay? You're giving something to someone, garbage, but you have to pay them money to take it. Okay? That's actually a really nice example. You could also think of the other way. You could think the product is actually the service of disposing something, and then you're paying positive prices for that. But it's a definitional issue. There's, for instance, electricity. You will always pay a positive amount for electricity, but wholesalers, because how the electricity market is done, because you always need to balance supply and demand in the electricity market, otherwise the frequency will go off and your phones, which are plugged in, and computers will get destroyed. That means that sometimes you're being paid to take electricity because you need to stabilize the market. So sometimes electricity has negative prices, but that's only at a wholesale level, okay, for big companies. which by that. But often we will have sensible restrictions like this, okay? Or it may be the positive number 4, that may be the capacity of a firm. We need to find out how much we're going to produce right now, but right now our factory will at most, even if we work 24 hours as fast as we can, produce 4,000 or whatever units, okay? So it means we're now making a decision of how much to produce now. It can't possibly be more than a certain amount. Okay. So, it means when we're thinking about functions, we always have to be very clear of where x is coming from. Okay. So we call that, where x is coming from, we call that the domain of a function. Okay, that's the domain of a function. And we sometimes abbreviate that with d. Okay? And it's the values for x on which f is defined. This is called a domain. Okay? So here we have another example where the domain says that x should come from the interval 0, 4. That's what the same interval we had before. Sometimes we then just say d is that interval. So then there's this other term called the range. Now, the range is what possible outcomes your function can take. Okay, so if you think about, so we have our rule, our function here, 3x plus 4. We have our domain. And if we plug our values in here, we get a range of possible outcomes. And we can, of course, think about this, okay? All of you possibly know what this function is going to look like. 3x plus 4, that means we have an intercept of 4, and then we have a slope of 3. Okay, so that goes fairly high up. And at a value of 4, what do we get? 3 times 4 is 12, plus 4 is 16. So if 4 is here, then this outcome here will be 16. Okay, so this is our function, but the domain is only between these 2 points. Okay, you could think of this function going on, but our domain is this one. And then we can see the outcomes our function takes is values from 4 to 16, including again, okay, from 4 to 16. Okay, so the range is 4 to 16. That's all the possible outcomes. So, it's very important to remember the definition of a function is incomplete unless you say what d is. Sometimes, so here we constrained it despite it not needing constraining from a mathematical point of view, right? Because we could have plugged in values of x smaller than 0 and values of x larger than 4. Mathematically, that was fine. Sometimes a function has a domain, a restricted domain, due to the mathematical nature of the function. Does someone remember a function which has a restricted domain? Yeah? Can you speak up a little bit, please? Sorry, I still didn't hear you. Can you speak up a bit? So super, okay? Logarithmic functions. And what was the restriction? We can't use a negative number inside the logarithm. Okay? So that's a natural restriction for the domain. And if a function has such a natural restriction, then we often don't state it. But that doesn't mean that there isn't a domain. It still has a domain. It's just a domain which is implied by the mathematical functions. We'll see examples of this in a moment. Okay? Here's another example of, if we are selling products, we can't sell negative numbers of products, usually, unless perhaps someone can think of an example. Okay? So, let's get your thinking woken up. I'll give you 3 minutes to think about the domain of these functions. Talk with your neighbor. This one is easier than this one. So think about one only. Okay? If you feel very confident, you can think of this domain. If you want to get started in your thinking, try the first one. Okay? So with your neighbor, 3 minutes, talk about this. So these are examples of natural domains where the restriction comes from the mathematical function. Are you good? Okay. Okay. Let's get back together. It's perhaps easiest to illustrate the argument looking at the graph. Sorry, I swapped the order here. So this is the first one on the right-hand side. So what is the restriction imposed by this function? I saw you guys here, you had it. What was it? Sorry, no, you got, no, sorry, we are talking about G, the one on the right-hand side. Did you have that as well, I think? That's right, X cannot be -3, and why?
Because if it was, then it would be a 0.
That's right. So here, remember we are having a division here, and we cannot divide by 0, right? Dividing by 0 is just not defined, doesn't work. So we have to make sure that this guy down here doesn't become 0, and that means X cannot be equal to -3. Okay? So whenever you have a division, a ratio in a function, that's one of the natural impositions you will have, one of the natural restrictions. So -3 is about here, right? Okay? So that's also actually because the slide told you to, I didn't tell you, think about the range. So this is the domain, okay? So you could say X for the domain, X element of the real numbers but without -3. That's one way. You could write it in words, but that's a short way how you could write it. Okay? Or sometimes element of real number but without x being equal to negative 3. So that vertical line means without. So what about the range? This term here, let's think about this term only for starters. If the number is larger than negative 3, what sign will this term take? Positive, okay? Now if we get very close to negative 3, what will happen to the denominator? If we get very close to negative 3, this becomes very small, right? Okay, so 1 divided by something very small becomes very big. Okay, as we approach negative 3 from here, that function will go to infinity. Okay, what if that number becomes very large? What happens to this term? Becomes extremely small. Okay, if x becomes very large, that becomes extremely small. It will approach 0. But now we also have that negative 5. So what will that whole term approach to as we get very large x's? Negative 5. Okay, so this is another important number here. So this function will go here. And you can use exactly the same sort of argument to figure out that if you have numbers, arguments smaller than negative 3, the function looks like this. Okay, rehearse that by yourself at home. So what is the range of this function? Yeah, the range is element of the real number, but without negative 5. Okay, negative 5 is the only value it doesn't take. So this next function is slightly more complicated because there are 2 restrictions imposed by the function. We again have a ratio, right? Okay, so what can that value not be? That cannot be 0, and that means that x cannot be minus 1. Okay? So something important happens here. And what's the other restriction? Pardon me?
X cannot be lower than 2.
X cannot be smaller than 2.
Because we have a square root, it has to be always a positive number.
Okay.
Also, x smaller than negative 1.
Okay, good. So x has to be larger or equal than 2, right? But it can also be, or, what did you say? But it could also be smaller than negative 1. Because if it's smaller than negative 1, then this will be negative, but this will be negative 2. And then this entire term will be positive. So here, the important errors are here, okay? So x has to be larger or equal to 2, so we are including the 2, or smaller than negative 1. So the domain of the function is, so here's the domain, and that's how you can write it, okay? And I'll leave you for you to figure this out, the range. The function looks something like this. Okay? So the range of the function will be from 0 to infinity. Or you could say element of real numbers plus. Okay? No, actually, because it also includes 0, we usually don't use that. So use this one. Sorry, use this one. Okay, so This is the sort of stuff you have to think about when you think about functions. Okay? Yes?
I have a question about the range. I don't think the range can. The 1 is included.
So 1 is not included, you say? Yes, I think you're absolutely right. Okay? Sorry. And why are you saying that?
Because I think that inside the square, it also equals to 1 minus 3 divided by x squared.
So,
So it can never approach 1.
yeah. Another way of thinking, super, thank you. I was being too quick here. So this is what it looks like. Think about the only way this function can be 1 is if inside the square root we have a 1, right? Because the square root of 1 is 1, and there isn't any other number of which the square root of is 1. But could this term here ever be 1? No. This term could never be 1. Okay? So this will approach 1 from below, and this will be just above 1, but then going to infinity. Thanks for watching me carefully. If you don't immediately get this argument, is that fine? Yes. Okay, because remember what I said last week, I don't expect you to come out of this lecture and think, oh yeah, everything is honky-dory, don't need to do anything. Okay, this lecture is just one part of your learning process. So if you're not fine with this, you need to sit down, and do you remember what you had to do with functions to figure out what they look? If you can't picture them, what do? You plug in values. You plug in different values for x and understand what it looks like. Okay? The more you do that, the better you get in understanding. I had to do this with this function as well. Okay? That didn't immediately appear to me. And of course, if you, as I propose you do, learn how to use Wolfram Cloud, this is the command to plot this function, and then there will be a similar command to plot this function. Okay? Remember, I advertised that I recommend that you use that so you can plot functions easily. Right? But you may have other means of doing so. So, this is a slide I will really basically jump over because it's about solving quadratic equations. You have all done that, but it will become important again, okay? So you need to be really sure you can do that, okay? You may remember that there are different ways of solving quadratic equations, depending on whether it looks like this, right? Where you have an a in front of the x squared, but sometimes, so I, for instance, in high school, I learned something like this. Okay, I learned to solve it from that form. Doesn't matter. Whatever is your preferred method, you can do so, and you will just have to go back and remind yourself how to do that. Okay, and again, I will have an online clip which talks about these two results. Okay, and that goes through the online clip, will go through this. Okay, so don't tell me we haven't done that. You will have done it once you looked at the online clip and see me go through this. So, there is now important functions which we need to know, classes of functions. The first one is what we call polynomials. And a quadratic function is a polynomial. It's a polynomial of order 2. Okay, we always look at the highest power, and that's what we have. Quadratic is a polynomial of order 2. We will often have higher order polynomials, for instance, a cubic function, where the highest power is 3. Now, cubic functions if you have the simplest of cubic functions, that will look like this. But this one is a cubic function as well, okay, because we have 3 factors here. If you were to factorize this out, you would get x times x times x, so x to the 3, plus lots of other terms. Okay, so this is a cubic function as well. It will have sort of the general shape similar to that. Can we see what the roots of this equation are? Remember, the roots are the values of x for which this function takes a value of 0. Okay? The x's which make this function 0 are called roots. So this is written in a form where it's very easy to see where the roots are. Can someone give me one? -3. Super. Because if that turns -3, this entire term is 0, and hence the whole thing is 0. Okay? So -3 is a root. Then we have -1 and 2. Sorry. Yeah, x equals 2. Okay, so then in some sense all you need to figure out now is if you have values smaller than -3, do you have negative values or positive values? Okay, now it turns out, again I'll ask you to do that by yourself to confirm this. Turns out this function looks something like this. Okay, has the general shape of a cubic function. Typically it goes to -infinity on one end of the domain, and it goes to positive infinity on the other end of the domain. So, again, this is, I didn't expect to get this far, in fact, so I've already uploaded the clip, but I'll take the last 2 minutes to give you an introduction for this, but that will supplement what we have online. So, there's something which is called a natural exponential. So we could take any little number a, we could take to the power of x. So what do we see here? We see that the argument of the function is in the exponent. Right? It's a particular type of function, but nothing prevents us from doing this, writing down a function where the argument is in the exponent. So that could be, let me give you an example, that could be 0.5 times 2 to the power of x. I just made this up. Okay, that's a perfectly valid function. If this number here, little a, takes a particular value, this one here, then we call that the natural exponential function. And this function just has a lot of nice features. Okay, then the function is, we write it as e to the power of x. Or sometimes also the exponential of x. That's the same thing. These two things are the same thing. Okay. And this function, it's special because it turns out that all sorts of natural processes can be modeled by using some version of this function. Okay, that's why it has sort of arisen as a very important function. And it has a number of properties. And let me start, and these you really need to know. Okay, the first property is this one. Exponential to the power of x, whatever the value of x is, it will always be positive. Right? Whatever you plug into this function, the outcome is going to be positive. Exponential to -10 will be a positive number. And let me show you how it plots. Okay? At 0, because e to the 0, any number to the power of 0 is what? 1. Okay, so that's why we have it here. Brilliant. If our argument is smaller than 0, that value will become smaller and smaller, but it will always stay positive. And if the argument is larger than 0, that value will very quickly grow to infinity. Okay? So this shape has to be burned into your mind because it's important to understand it, to understand many functions. Now, for the rest of these details, and indeed for the details of the inverse of the exponential function, which is nothing else than the natural logarithm function. Okay, and then actually, let me just plot that. This looks like this. Okay, and as one of you said before, this isn't defined for negative values, only defined for positive arguments. The properties of these two functions you really need to know. Okay, and you start by looking at the clip online, which is in the Inside This Week section, and then of course there will be practice questions. So, remember how this course works. The lecture is one part, but what I ask you to do on the Blackboard side is equally important and equally examinable. Okay? So, go away and I'll see you again on Friday. Of course you can.
If you say that this function can never be 1, does that mean that you need to add and not 1 to the domain?
I should have done that. I've only said it verbally. I should have put it on the slide. Yeah.
Okay. So you just write a comma and then not 1.
Yeah, or vertical, either that, yeah, or you can say a vertical line like we did it here, and not 1. Good point. Yes. We don't